So, hello, welcome back. I'm very glad that you gave up sunshine outside and came to listen to the presentations, which hopefully will be very interesting. In this session, we are trying to combine two subjects, a bit of security and a bit of monitoring, and see how one can benefit from another subject, how they can complement each other. And let me introduce the first speaker of the session, Peter Haag from Switch CERT. Peter does many interesting things for the CERT, and among them, one of them is development and improvement of software NFSen. And in his presentation, you'll hear a lot about it and not only about NFSen. So, Peter, please, floor is yours.
Many thanks, Baiba, for this introduction. Okay, here we go. Let me introduce the agenda first. I'd like to give you a reason why we think about NFSen and Netflow. So these are some operational questions we ask. Then why to use this Netflow stuff at all, the tools we use, NFSen and NFDump, which I developed, and then how to track incidents with these tools, which is in the end the goal, what we want to do. So these questions are really security related from a CERT perspective. If you work in a network operations center, then you may have similar questions or maybe the same questions. They pop up every now and then, and if you operate the network. So what caused this peak, and could you investigate this incident, and please help us doing this and that. And we all need to find answers on these questions. And so that's the motivation at all. And what we all have in most all network operation centers are graphs like that. However, graphs like that is very nice to look at pictures, because pictures is always nice to look at, aren't they? So, but they do not give enough information to give an answer on all these questions we have. So the traditional monitoring is no longer what we need to. So we need to go one step further, and more information is really required when we focus about answers on our questions. So we need IP addresses, we need port information, we need flags, for example, we need interface numbers, AS numbers, all these information which is also available by SNMP queries, for example, or part of that information. And luckily enough, Netflow can help you to answering these questions, because all these information here which helps us to answer these questions are available in Netflow data. So what is Netflow? I think I do not have to dig into the very details, because this is a network conference, so I guess everybody almost know what Netflow is. However, a brief description of that. We have that's a technology developed by Cisco, and we have all these additional information in the Netflow data. One very important point to note is Netflow data up to now and up to as V9 was defined, no user information, so no payload information is available. So privacy of the user data is always respected with Netflow data so far, as it concerns the content of the data. So you see one line here, for example, how the Netflow might look like. You have a date, you have the protocol, then you have IP addresses, port numbers, packets and bytes, and so you have looks quite familiar if, for example, you have TCP dump or Argus, for example. What Netflow versions are around? This is just a brief overview to point out that Netflow is not only available in one single version. We have a lot of versions available, and the most popular one is V5. So most people who deal with Netflow data mostly use V5 Netflow data. However, V7 is used as well, because a lot of Catalyst switches still use Netflow V7. Then the newer one, the template-based one, is V9, which is nowadays coming more and more. And the reason for that is Netflow V9 is very flexible. And so you have a lot of more additional information available, for example, IPv6, for those who are working with IPv6. This might be a reason why you want to migrate to Netflow v9 instead of v5, because v5 cannot deal with IPv6. So let's give an example how these Netflow records look like. When you look at the simple connection from a client to a server, you have the traffic from the client to the server and the traffic from the server to the client. After the handshake, you send some data to the web server in this example, and you get an answer back from the web server. So in the end, this results in two different flows. So flows are only unidirectional. They point from one IP address to another IP address. So you have always two flows, one from the client to the server and the other one. So where do we now get these Netflow data? Yes, of course, routers can provide Netflow data, and you can go onto the router, telnet or SSH into the router and do a show IP cache, and you get all this information about Netflow data as it is currently in the router available. However, if something happens at weekends, you almost never have this information then available, so you need some other mechanisms to collect and store the Netflow data and process it afterwards. And that's why NFSyn and NFDump now come into play. So NFSyn and NFDump are two different tools which are related to each other. You see at the bottom NFDump, which collects the data, which does all the Netflow processing, and then on top of that we have NSN, which displays all the nice pictures, which allows you to do profiles and so on. So that's the way the two tools are hooked into each other. Again, how does it work? On the left-hand side, the collection of Netflow data. You can have v5, v7, v9, whatever. There is also an SFlow collector in the tool package for those who have SFlow equipment. You collect all the data and put it in a storage. After that, the version of the Netflow data is no longer important, because internally it's stored in its own format. But then you can process all the Netflow data with NFDump later on at any time you want for any output you want. The features of NFDump: if you are used to work with TCPDump, for example, then you are very fast familiar with NFDump, because the command line syntax of NFDump is very, very similar to TCPDump. And also the filter syntax is very, very flexible. It's a kind of TCPDump. It's not the same PCAP syntax, but looks very similar and adds additional features which allows you to access other fields for Netflow data which TCPDump can't do. For example, source port greater than is easy, or the number of bytes in the Netflow records smaller than or bigger than whatsoever. So the syntax is very flexible, as we will see, which is also needed to find an answer on our questions. So that's how things look like when you simply list the flows. You see that the IP address, the dates, the protocol, source IP address, destination IP address, number of bytes and packets. So you have an easy overview how simply flow listing looks like. In the middle or in the lower bottom you see IPv6 addresses, how they look like in NFDump. So you can also process IPv6 data very easily with the same commands. There is no difference between IPv4 and IPv6 internally. You can also create top 10 statistics. For example, let's find an answer on our question: who is consuming my bandwidth? So you create statistics, top 10 statistics, and order these statistics by IP addresses and bits per second. And the answer is what you find here. And you see the IP address consumes quite a considerable amount of bandwidth, which can be very easily evaluated just by using one query applying to the Netflow files. A more complex example is shown here. If you want to have any candidates for port scanning, for example, then you have to process the flows totally different. We need another type of aggregation. First, we have to understand what we want to look for. So scanning means I have the same source IP address and have always the same destination port. So what I do now is I aggregate the flows by source port and destination port, and anything else in between is not interesting for evaluating the scanning candidates. Then I say the scanning candidates have only a few packets, only a few bytes in the flow. So all these can be added in the filter. Then I can remove some of the false positives I might have. And the output is a list of possible scanning candidates, which you then can dig further into the details or evaluate, is this really a scanner or is it not? But with a one-line command with a not too complex filter, you can already have information like that available. You can also aggregate on subnet basis. For example, if you want to know which subnets exchange most traffic with each other, so it's no longer a single IP address, but rather entire network blocks. In this example, we compared the /24s for source and destination, but of course you can have any aggregation /8, /16, /727, whatever you want to have, to see how much traffic is going to be exchanged from that network, not only a single IP address. A nice feature in up from 1.5.6 on is that you can use host names. For example, CNN.com has a lot of IP addresses assigned, and if you look into your flows, who connects to, in this example, CNN.com, you would need each single IP address and form a filter to look at that. But here it's very easy. You simply say, I'd like to have all the flows connected to CNN.com, and it forms automatically a filter from what the DNS lookup brings back. So this filter is created internally. This was very easy, for example, for fast flux networks, for those who were dealing or are still dealing with fast flux networks. IP addresses, there are a lot of IP addresses per host, and they may change very rapidly. So this is a convenient way to track these kind of flux nets. As you have seen, everything is a kind of art of filter design. You need to understand the problem, and you need to understand what you want to look at. And if you have that, then you can formulate the filter with the appropriate syntax. And it is important to see that all these tools, they do not do your job. They simply support you in doing this job. They do not give you an answer, who is the bad guy. You need to formulate the questions to figure out which is your bad guy, or who consumes most bandwidth, for example. So we have seen the tool is very flexible, powerful. You do everything on the command line as you are used, for example, with TCP dump, or if you are on a route doing everything on that stuff, you are used to work with nfdump. However, as I already said at the beginning, pictures are very nice to look at, and they give a lot of information, and maybe more information at a simple glance when you're looking at the pictures. And that's the point where now NFSyn comes into. NFSyn has a lot of nice features also for incident analysis. It uses what we already know, these backend tools, nfdump, for doing all this Netflow processing and collecting. You have the pictures we want to look at. You can drill down from an overview to the individual flows, which I will show you in a moment. You can graph network situations where you're mostly interested in, and so on. You can analyze specific time windows you are interested in, so you can go very detailed into the flows. When you start up NFSyn, it looks like that. So you have 3 columns. You have the flows, the packets, and the bytes. And if you already look at this kind of graph, you can already distinguish what's going on in your network, for example. If you see a lot of bytes, look at a red peak on the right-hand side, for example, and you have a lot of packets, but you have almost not the same peak in the flows, you can also make an assumption what it is all about. So we have a large transfer with a lot of bytes, a lot of packets, but this fits all in 1 or 2 flows, for example. So there is no much difference in the flows. This might be a legal transfer, legal video conferencing, as we find it in our networks. So by looking already at these graphs, you can have one hint and can check the health of your network. But then you can go into the more details. Here we see in the main graph in the middle, you have the packets, which is then split up into the protocols above the graph, the small pictures. You see the protocols TCP, UDP, ICMP, and all the other protocols are put together in a graph. And in this example, you see, okay, this peak we have seen is in protocol UDP. You do not have to investigate further on. A simple look at this graph is enough to spot in which protocol you have to look for. Also, the different color you see here are allocated to different Netflow sources. Each Netflow source you have and collect your Netflow data can be assigned a different color. So you can easily identify which Netflow source this data comes from. Then you also have a little table below where you again see the colors, and you have the real numbers. When you are interested in the numbers, you see them easily in the selected time slot. When I go back, you see a cursor which is now positioned in the middle, and for this cursor you see all the data in the table below. Now scrolling down this screen, you can then further do your Netflow processing. In this example, I calculated the top 10 statistics of this selected time slot, and the output is the familiar list of NFDump. So that's where NFSend and NFDump hooked into each other. And the workflow is therefore very easily. You have an overview. You start with packets, bytes, flows. You then go into the details. You select your protocol, you select the time slice where you are interested in digging into the details, and then you go into the flows to see which IP addresses are affected, and what's the number of packets and bytes which really were at this time slot. Let's make an example with this red peak we already saw. So we see it's UDP, so we click on the UDP picture. This exchanges automatically and puts UDP in the middle. Now I see on the right-hand side the flows and the bytes, and I see there is also a lot of bytes, so I click on the bytes graph. We see, okay, that's more than a gig traffic we have in this example. I position the cursor somewhere in this peak, then I scroll down and say I'd like to have now the statistics from connections in this selected time slot, and what I get is the table like that. So I see I have a few connections on the top, and in this example it was nothing bad, it was simply video conferencing which was held between two sites. So far what we have observed is all these peaks are visible in the entire flows, and they can be spotted very easily. But this may not always be the case. So, for example, if something is going on in the mass of a lot of packets and bytes, you can't spot it here in these graphs. So this might be difficult to detect, so we need some other choices. I will now refer to a practical example how this could look like, for example. This was a real case, and it was spotted like that. Hello, CERT. We experienced a Syn Flood attack towards our web server, and do you have similar events in your network? If so, have you any details for that? And so on and so on. The offending IP address was 1234, and which we finally blocked. That's the information we get, so deal with that. So I looked at the NFSend graph, and looking at the picture didn't really reveal anything obvious, and so that's now the reason where profiles come into play. We need now to make a profile for what we are looking at. And what is a profile? A profile is a specific view on the Netflow data, but we have already filters applied, filters what we are interested in, and leave out everything else we are not interested in. A profile can be specified from flows we already collected in the past, or it can be created from ongoing processing flows as they come in. So we have a very flexible options to create these profiles. For example, you can also display these graphs differently. On the left-hand side, you have the total traffic situation, and on the right-hand side is a profile which shows you the very same traffic, but divided into input and output. So this is a very easy profile, but you can go much further. And so let's make an example for our incident we have. What we are looking at is the IP address of the offending IP address and the IP address of the web server of the customer, which he reported to us. And the result of that was the picture on the right-hand side. Okay, now we see something more. There is something we can spot now. Going into the details, we see the attacker, the so-called attacker, the offending host, appeared first on the left-hand side. That's where we see the first flows. By the way, the blue color is what you see, the web server input and output traffic, and the other colors are from the offending IP address. So you can also distinguish according to the colors what's going on here. So you can easily spot that's the point where the offending IP address appeared first. Then we see an event, a time slot where the so-called Syn Flood Attack started. And then we see an event on the bottom side where obviously the IP address was blocked. So the information given by the customer matched at least what we see here in this profile. But are we now done? No, we are not. So we now want to have a look into this incident. We now want to look into the flows. Now we have spotted a time series, and we see there was really something going on, and we now need to dig into the details here. What we now do is we take a time slice. You see that on the right-hand side there, at the very beginning, where the offending IP address started first, and list the flows, and let's see what we see here. And the flows show that this is more or less traffic accessing the web server. There is nothing suspicious here, really. A few accesses to maybe a few pages. You see the transferred number of bytes looks reasonable to us. This might be web pages. So at that point, nothing seemed to really to be suspicious. Now we have a look at the event where we see at the peak in the graph, and at the point where the so-called Syn Flood Attack might have come into play. When listing the flows, we see, okay, there's something going on. We have here the answers from the web server and not some attacking packets. And we see that on the right-hand side there is a lot of bytes which have been transferred, and all these bytes do not look very suspicious. So it seems as this client really took massive amount of data from this web server, and the web server really answered all these queries. So there is nothing about Syn Flood attacks, even if we have no flags here, because the exporting source does not support flags. And so we have no information about that. But anyway, we see that the data transferred here is not, or does not look like an attack. And so we came to the conclusion and phoned back to our customer. Hello, we could spot your event you described, but the IP address in question might be a client which did massive gets from your web server, or a mock running client or whatsoever. So you might see any hints in your log files, and later on the customer really confirmed what we suspected it is. So it is not always what the customer pretends to say it is. So you need to have good tools to dig into these details and see what's going on. I'll give you a brief other example from a hacked host, for example, which we also tracked. You see here on the right-hand side, suddenly there is traffic from a host which had for a very long period of time almost nothing, and then suddenly starts. We also profiled that host, and we looked at the time window you see here, spotted into the flows, and what we saw here is that there was an SSH connection to that host, and almost after the SSH connection we see an FTP session, and then we see more SSH traffic there. So what happened here, you see really the traffic of the attack. This was an SSH password guessing attack, which was successful. Then the attacker downloaded its own toolkit using FTP, and by the way, you see then also the IP address where this toolkit is stored, and then he started scanning the network with SSH again. So it was a kind of malware spreading from host to host, and These things can be easily tracked and spotted by using flow data and creating profiles. There are other issues and possibilities how to detect incidents. You have a lot of alerts or possibility to write extensions. We saw an example of an extension in a track yesterday, for example. I do not want to go for time issues into these alerts and extensions, but if you are interested in writing your own code, everything is on the web. You can get all this information, how to write extensions and how to program your alerts. That's everything available on the net at SourceForge. So again, to summarize, pictures help. Create appropriate profiles if needed. So sit down, think what's the information I need, and create a profile about that. Check your flows carefully, because they almost tell you anything if you look carefully at them. And again, don't be fooled what customer tells you. Tracking incidents is always, the last sentence here is also very important. For tracking incidents, it is important to have unsampled flows. Otherwise, you obviously miss anything. I know this is, for a lot of networks, this is a big issue, and a lot of big networks have to sample because of the infrastructure. There's no other way around that. However, if you have a smaller network, or if you have parts of the network, you can afford not sampling and tracking incidents. This would be an option to do so. So the future of NFSen. NFSen is still in development. Newer versions will come. And also NFDump will be involved. NFDump, for example, will have more V9 tags. It will be almost complete V9 implemented, also for flexible Netflow stuff, for those who know what I'm talking about with flexible Netflow. Then we have bidirectional flows in the new version of NFDump, so you instantly see the traffic between both affected parties, so you do not have to grab the flows, which one is exchanging with which one, which flows go together. Also, NFSen will have a lot of new features. There are a lot of ideas from users which are coming along. We will have user authentication, customized pages, visualization, as you see here, a possible example. For those who are interested in visualization, that's a big, nice toy to play with, I can tell you. What you see here is the traffic of the RBN network at the time it was alive, and it affected the network. So you can easily spot, okay, these are the bad boys, and all these blue ones are infected hosts. So you can have an impression how, for example, a network might look like, or something like that, which is nothing else than port 25 traffic. If you want to spot your spammers and who has a lot of connection outgoing or incoming connections or whatsoever. So it gives you a visual impression, and pictures are very important to give the right information to the user, because it can instantly transfer information to the person in front of the screen. As a summary, Netflow is really useful for tracking incidents and also for getting out information about your network. Use the right tool for the right task. I have presented you NFSen and NFDump as one of them. They are both free tools and available on SourceForge. So they run under any Linux, Unix whatsoever. They are easy to install, and that's it for this presentation. Many thanks. Okay.
No questions? Everything is clear? We all will use Netflow and yes?
Everybody's happy.
No questions? Okay, I thought there is something at the end. Thank you, Peter, very much. And let me introduce the next presentation. It will be given... Oh, no, I thought there is a question, but everything is clear. So, the next presenter is Valentin Carrera Espanyol. He is from Barcelona, and He is research assistant in the computer architecture department in the University of Polytechnical University of Catalonia. I know that he spent a couple of months in Ghent, so this area is not so unfamiliar, and I hope that will be encouraging to give the presentation, which will be about identification of network applications based on machine learning techniques. So, the floor is yours.
Thank you for the introduction, Baiba. I'm going to explain a work that I did with Pere Barlet Ross under the supervision of José Soler Pareta about the identification of network application based on machine learning techniques. The outline of this presentation will be this one, with the first part of motivation and objectives of the project. Then I will explain the scenario and the requirements of this project. Then I will explain the existing solution, the state of the art of the identification of application in traffic network, and then I will explain our method that we designed. And at the end, I will explain the summary and the conclusion of this project. The main motivation of this project was that the typical method based on the well-known ports from YANA is no longer valid due to the big inaccuracy that it has. The main objective of the identification of this traffic is to help in the network administration and also in the management tasks. But basically, it's used for the quality of service monitoring, for the classes of service mapping, or for make policies, or maybe for a possible way of pricing for quality of service. Then the scenario where we have to deploy this solution is the Smart Shack. I'm not going to enter in detail because it was explained in the Terena 2006 by Pere Barlet. And this is a tailor-made traffic monitoring system for the Anella Scientifica. The Anella Scientifica is a network, an educational network with the universities, schools, and research institutions, also some hospitals from Catalonia. And the main objective of this monitoring tool is that it's a low-cost platform. It continuous monitoring of high-speed links without packet loss, and it's linked to detect network anomalies and irregular uses. This tool is measuring the link between the red iris and the Anella Scientifica. This is the scenario of the Smart Shack. We have two splitters in the link between the red iris and Anella Scientifica that send the traffic to the capture system that have two dark networks. And in the capture system is done the first aggregation in flows with the protocol, the source and destination address and ports, and also the packet, the number of packets and the number of bytes. Then in the traffic analysis, that is the more computationally or critical point of the Smart Shack, is done the analysis of the traffic, for example, for the top-end direction, or that they consume more bandwidth, or for example to find out anomalies or something like that. And in the last machine is where we show the results of this analysis. The requirements that we have with this scenario, we need a solution that could work in real time. We don't have to access to the packet contents. It have to work in a high-speed links without packet loss, and it have to achieve a high accuracy. And this solution have to be adapted to the architecture of the Smart Shack. Then, in the state of the art, I make 3 groups. I know that there are some papers that explain some some solutions that are not belonging to any of these groups, but I have no time to explain each one separately. So let me say that the state of the art of the identification of application is like a race with two runners, one of them the application, but basically the peer-to-peer application, and the other runner are us or the researchers of this kind of topic. When the race starts, we have the solution or the method of the well-known ports. That is a very simple method that use the ports from the register from IANA. And it's a simple matrix that for every port or every known port, it has the application. This solution doesn't need the packet expansion and is very computationally lightweight. But it has a lot of limitations, especially due to the new peer-to-peer application that have some features like the use of dynamic ports or use the port 80. Or, for example, also that new application don't register their ports in the IANA register. So, as a consequence, we have a very low accuracy. As you could see in this example, this is the example of the well-known ports in the Smart Shack, where we have more than 60% of the traffic that it's classified as unknown. And also we have more than 21% that it's classified as web traffic. Maybe a part of this web traffic is peer-to-peer, or we will find out. The next step was the payload based or pattern matching that the researchers find out to identify the most of peer-to-peer application. And this method tries to find characteristic signatures in the packet or flows payload. This method achieves a very high accuracy, but it has some limitation. The main one is that it's computationally expensive because you have to search in every payload for all the signatures that you have. Also, you need the packet content, so you could have problem with privacy legislation. And it doesn't work with connections that are encrypted. And also it's difficult to maintain update because you have to change the signatures for every version that every application changes. As a consequence, it's not a feasible solution in our scenario. Then appear the machine learning solutions that comes from a subfield of the artificial intelligence. And it's a process that allows computer to extract knowledge from examples, from a training set. The main characteristic of these solutions are that the packet context is not required. It also achieves a high accuracy, like the payload based methods, but this one respects the privacy legislation and also is computationally viable. The main limitation of this kind of solution is that it has a very difficult training phase, not very difficult, but in terms is a long training phase in terms of time, and it also has to be retrained occasionally. There are principally two types of machine learning solution. One of them is supervised learning, also called classification, and this technique creates knowledge structures that classify new instances into predefined classes. The knowledge layer could be presented as a decision tree, that is more common, also as a flowchart or a classification rules. The training dataset that we need to make this method consists in a tuple of two objects. The first one is a vector of features characteristic of this instance, and the second one is the value to be predicted that we have to label manually. In our case, the vector will be a features from the packets or from the flows, and the class will be the application. As you can see in the tree, in the decision tree, for example, x1, x2 will be the features, and A, B, C, D, E, F, and F will be the application. The other method is the unsupervised learning, or also called named clustering, that tries to find out the best partition from similarities among the examples. In this case, you don't need the labels for the training phase, so you only need futures. And there are three methods for make the clustering: the Cummings algorithm, an incremental algorithm, and probability-based algorithm. As an example, you could think, for example, that the pink color cluster is a peer-to-peer application, and the green one is the web traffic, for example. We have in the decision to choose which one to implement it in our scenario, and we have for the supervision method that need a complete pre-labeled data set. So every packet or every flow that we have in the training set have to be labeled. But it has a better accuracy for predefined classes, but it not detect new classes and have difficult to detect when it's necessary a retraining. In the other hand, the unsupervised methods do not need complete labeled distance, but also it have automatic detection of new classes, and it achieves better accuracy with new classes. Another important point in the machine learning techniques is the feature selection. With some methods, you can detect irrelevant or redundant features, and that achieves you to improve the accuracy and reduce the computationally load. There are two types of feature selection. One of them is the wrapper method that depends on the machine learning algorithm that we are going to use, and they evaluate the performance of different subsets of features with this algorithm. An example could be the correlation-based feature selection. The other method is the filter methods that are similar to the wrapper, but they do not depend on the machine learning algorithm. They make the assessment based on the general characteristic of the data. Then we are going to explain our proposed method. We implemented a supervised identification based in the C4.5 algorithm that is developed by Ross Kinlan and as extension of ID3. It's based on the construction of classification tree, and to make the future selection, we use maximizing the information gain algorithm. The training set that we are going to use is with actual traffic flows, with a vector of flow features, and we label it with the application correspondent. And this application of each flow will be identified manually, or maybe with a pattern matching method. The features of our training data set have two requirements. One of them is that we have to take these features in real time, and the other one is that these features have to be independent from the packet contents. And an example of some features that we could have would be the packet and bytes per flow, flow duration, minimum, average, and maximum packet size, average sync ratio of IP, OS estimation, and also ports and protocol, but not in the same, not as in the well-known port solution, in another way. So the training phase of the machine learning solution that we are going to implement have the first part is the collection of training traffic. We need a representative of traffic of the environment that we are going to be monitoring. In our case, the Anella Scientifica. Then we will make a flow aggregation, and also the feature extraction of in the flows. Then with the flows, with this feature extraction and the flow aggregation, we will labelate this instance using a pattern matching algorithm like the layer 7 filter. And if there is still some instances that are not labeled, we have to make manual inspection of the rest of flows to label it. For example, with NetFilter or another software like this. If we had a problem for example, we don't have enough traffic from games or from peer-to-peer or from, I don't know, peer-to-peer is not the case, but from games, for example, we can generate artificially traffic under a controller environment. And 2 points interesting of this solution is that there is no manual identification and solve encryption problems, but it's not a real solution. It's better to take a representative environment to be monitored. Then the second part is when we have the features of every flow and the application for every flow. We construct the C4.5. We use the C4.5 algorithm to create the decision tree. And to do it, we use a software named Weka from University of Waikato from New Zealand. And it's open source and it's written in Java and it's very easy to use. Then when we have this decision tree, we will implement it in the traffic analysis machine. But before, we have to reprogram the capture system to extract the features. And with this solution, there is no need to analyze the packet contents. We don't have to trust only on the port numbers. Also, we don't have to apply pattern search algorithms in the real time, and we don't need to spec manually packets. But it's required to retrain the system occasionally due to the apparition of new application or the change in existing ones. With this method, we achieve accuracy nearly to 95%. We have some case like the news or Linux groups that are nearly to 80%. Maybe due to the reason that we have less flows than the other case. And if we make a comparison with the port basket, we will see that more than 40% of the traffic is peer-to-peer, and the 19% is for web traffic. So the most part of the identified unknown traffic from the port basket is a peer-to-peer traffic. You could think that this 40% it's not a lot of traffic of peer-to-peer traffic for a network, but you have to think that it's an educational network, so I think it's enough, 40% of traffic peer-to-peer. This is another graphic. On the first one, the orange part is unknown traffic, and in the second one, with a machine learning solution, we only have 0.3% of unknown traffic. So a summary of our solution for make a machine learning method. We have to collect the data for a training data set. We need a representative flow of the environment. If we don't have, we can generate artificially this traffic. Then we make a feature extraction from the training flows. With this feature, we will match every flow with his application. We could use pattern matching or manual inspection, for example, layer 7 or NetFilter. And if we use traffic generated artificially, we can jump this step. Then when we have both the features and the application, we construct the classification tree using Weka, and then we have to deploy the tree obtained in the step 4 in the monitoring system. And after some time, we have to retrain the system, and it will mean that we have to start from the point 1. As a conclusion of the presentation, I think I can say that the traditional method based on well-known ports is no longer valid because it has a low accuracy due to the use of the dynamic ports. The identification based on pattern matching could be a solution, but no in our case because it depends on the packet contents and it's not feasible with high-speed links. And it also doesn't work with encryption. And the identification based on machine learning, it's a feasible solution in high-speed links. Does not require packet content, and it achieves a high accuracy, greater than 95%. But it has a problem that it requires an occasionally retrain. As a future work, or maybe a present work, we are retraining the method with the new scenario that we have now 10 gigabytes instead of 2, and we are trying also to make the training phase as automatic as possible. Thank you for your attention.
Hi, a question which is also a suggestion for a possible future work. Mm-hmm. You showed all these features that require, by the way, packet capturing, okay? Yeah. What is your feeling? Have you tried what you can obtain with Netflow information only? So the information that you can obtain with Netflow?
We also are thinking to use Netflow for the identification of application, but as far as we try, we need more flow to achieve a high accuracy. We need more features that the Netflow gives us. So
you have already tried?
We try with the same flow that Netflow, the same features that Netflow gives us, but not with the Netflow software. We try to do this project with the IPs, the packets, and the number of packets and number of bytes, also the time, but with these features the accuracy was not very high.
Okay, thanks.
Other questions? Okay, thank you very much. And this brings us to the last speaker of the session, Radek Reggie. He is from Masaryk University in the Czech Republic, studying to get his master thesis and working already at least 3 years on the LibreRouter project. And he is going to talk about Netconf, a secure Flowmon probe remote configuration. So, welcome.
Thank you for the introduction. Good afternoon, ladies and gentlemen. I'm working for Subnet, and as one of tasks for Subnet was preparation of the remote configuration system, primarily used for our passive monitoring monitoring device named Flowmon. And in the following minutes, I'd like to introduce this system to you. So let me give you a little overview of my talk. In the beginning, I'm going to say about something about our motivation, about our possibilities in approaches to network configuration, and then I will try briefly introduce Netconf Protocol, which is developed by IETF as accessor of SNMP protocol. And main part of my presentation will a description of the system for remote configuration currently used for configuring the Flowmon probe. And then I will also discuss possibilities for reusing our system or some its parts for any other devices. And after that, I will discuss also some other future plans. So let's start by introduction, by motivation to prepare remote configuration system. A year or two ago, we have prepared passive monitoring device, and we have started to deploy it to network, but we had only some local tools to configure that, some scripts or specified tools, programs. So this approach can be good for development, for developers, but it cannot be used by end users. So we have needed some kind of system for remote configuration. You can see on the picture one part of the system is network configuration, but on the other side we needed also some pretty nice interface for users, which would be independent and accessible for different devices, for example, for PDAs, smartphones, as well as laptops. So for this part, it was supposed to develop some kind of web application. And for this part of network configuration, there are several possible approaches. First of them is SSH, Secure Shell. You surely know it's a powerful tool, but it's good that it's secure, but you still need some framework for managing configuration data. So it can be a solid base layer, but it needs extensions. Other possible approach is to prepare some kind of command line interface, widely currently used and built in network devices. But for us, it was quite bad idea, because we just prepared another vendor-specific interface. There can be problems if people have different devices from different vendors in their network, and they need to configure them. So they need also several tools, and there can be operations with same name but different meanings, and it's not good. So next approach can be prepare a system based on SNMP. SNMP is also widely used, but unfortunately almost exclusively as a vehicle for obtaining some statistics, obtaining device information. So finally we decided to use new Netconf Protocol, which is supposed to be an accessor of SNMP. And now I'd like to really briefly introduce Netconf Protocol. If you are interested in more detailed information about protocol, I refer to request for comments documents which specify this protocol. So Netconf Protocol is network configuration and management protocol based on extensible message on XML format for both protocol messages as well as device configuration data. It's a client-server protocol using simple remote procedure calls mechanism. Important feature is that protocol can be simply extended by defining new capability that modify existing operation, or it defines entirely new ones. And as I mentioned, SSH. So every Netconf compliant implementation must provide SSH transport. So it's a secure protocol. And just note about terminology. According to Netconf specification, when I will talk about Netconf agent, it's a server-side application, and Netconf manager is a client-side application. So the main part of the presentation is a description of the remote configuration system currently used for our Flowmon probes. System is implemented for Unix-like operating system, exactly for the GNU Linux system. The scheme of the system you can see on this picture. System can be divided into 3 separated parts. The core of the system is Netconf subsystem, which is client-server application. With Netconf manager on the client side and Netconf agent program on the server side. Next important part is configuration daemon, which control managed device, and last part is web configuration front end, which provides that simple, intuitive, and user-friendly interface for end users. So now I will describe all parts in more details. Netconf subsystem, as I said, it's a client-server application connecting both sides of the network configuration system. It uses SSH to connect both parts. You can see also on the picture that Netconf manager is then extended by graphical configuration front end, which is widely used by. But Netconf manager also contains its own very simple command line based interface. You maybe know from SFTP program. So Netconf manager can be used. Netconf manager and the whole system can be also used without configuration front end directly from your command lines from your console screens. Here you can see also currently implemented Netconf capabilities, which extends configuration data stores. Next part is configuration daemon. As I said, it controls managed device. That device can be also anything. We use it for controlling hardware card, but it also can be some software application. And therefore, configuration daemon is fully device-dependent part of the system because it must be adapted for managed device. Here you can see some functions which configuration daemon provides for our hardware card. It boots up firmware, configures and starts up firmware, reads various card statistics, and it also controls Netflow exporter programs. But as I said, it can be almost anything. Due to fully dependency on device, if you are going to reuse the system, you have to completely modify this configuration daemon for your device. But you have to preserve communication between configuration daemon and Netconf subsystem, which is currently implemented as a pair of named pipes in Linux. It serves as a pair of communication channels between Netconf agent and configuration daemon. And according to Netconf specification, and as you can see from picture, there is possibility to have multiple connections, Netconf connections to the device, to the host system. So there can be also multiple instances of Netconf agents. So there must be some mechanism to control accessing Netconf agents to configuration daemon. This is implemented as a special lockable file, say communication key. So when Netconf agent want to communicate with configuration daemon, it must try to lock this file, and if it succeeds, it can communicate. But at this moment, the access to the communication channels is for other Netconf agents denied. The last, as I mentioned, optional part of the system is configuration front end. Here you can see some screenshot on this screen. Front end displays some information about interfaces, collectors, and other information from device. Configuration front end is actually a simple XML generator. It's a web application, so it's platform independent and provides nice, user-friendly and intuitive interface for other users. On this and one following slide with a little scary picture, I'd like to try to simply explain how does the system work. So on the server side, there is configuration daemon running and controlling the device. But Netconf session is established by starting Netconf manager program, which prepares SSH connection to the host system by by executing SSH client program. On the picture, you can see the process of redirecting SSH standard input and output to prepared pipes, which enable Netconf manager directly communicate with SSH client. Started SSH client, then prepare SSH connection to the target host system of the device, and due to SSH subsystem mechanism available since SSH version 2, it also starts a Netconf agent on the host system. So since now the Netconf connection over SSH is prepared, and Netconf manager and Netconf agent can communicate to each other. This communication starts by sending hello messages containing a list of supported capabilities of each site, and in further synchronous message exchange, only common set of capabilities are supported and are used. So reusing system, as I said, there are some parts that must be modified to reuse system for other device. We are now using system only for configuration of flow mount probes. Netconf subsystem, which is core of the system, is device configuration data independent, so it can be directly reused, but you have to adapt some XSLT style sheets used for filtering and editing. Configuration daemon is completely dependent on target on managed device, so it can be completely rewrite and adapted for the device. And configuration from frontend is at this moment it's fully flow mount probe specific, but we are going to prepare new generation of the front end, which would be used for any device, for any configuration data, only by specifying some XML documents. These are some restrictions, but we have implemented the system for Unix-like operating system. So if you want to use it, for example, on Windows, you have to re-implement it and adapt it for Windows. Using XML format for configuration data, it's defined by a Netconf specification for using such features like Netconf subtree filtering. And as I said, you are completely free to use the system to manage hardware devices as well as software programs. Our future plans. Our ultimate goal is to prepare a framework which can be used to manage any device, ideally only by defining device configuration data model and maybe some other specification. but it's a long time plan. For now, we are going to add to the system, to the Netconf subsystem, implementation of the Netconf notifications capability, which is analogy to SNMP traps. It's asynchronous message delivery service, so you can then obtain information and notices from the device about some events happened to the device, happened to the network. So we think that this capability is really important. Then there are some other capabilities defined by Netconf specification, and we are also preparing our own system management capability, which should provide such operation like system reboot or firmware upgrade, and so on. So that's all. Thank you for your attention. I hope that everything was clear, but if you have any question.
Let's thank all speakers again. I hope you got something, some useful hints from this session, maybe something you can use back at home. Let me remind you about the evaluation forms which can be filled online, and you can express your opinion about the presentations you've heard. Tonight we have the dinner at 7:30. Don't forget to bring your coat, because the beginning will be outside. And don't forget your badge. And that's, I think, is all I have to say. We have time for early coffee break. Thanks for coming.